This is the beginning of Chapter 8, which focuses heavily on integration techniques and improper integrals. In this first section, Section 8.1, we're going to talk about basic integration rules. So really, I'm just going to show you several different examples of different types of integrals in order to help you complete your homework for this section. So the first thing I want to show you is just a list of different integration rules which can be found in your book, but I would make sure that these are at least familiar to you so that it makes solving your integral problems a little bit easier. So just know that you can always refer back to this slide if needed. Here is our first example. It says find the indefinite integral. Now, just a reminder, I know that this is an indefinite integral because I don't have any limits of integration. So remember, anytime you have an indefinite integral, you absolutely must remember to include a plus c. The integral will be incorrect if you forget the plus c. So in this example here, I have 5 over the quantity t plus 6 cubed. So in this case, if I have some function to a power of n, I'm just going to apply this general power rule. So it would be helpful to take this constant and move it out in front. So this becomes 5 times the integral of 1. Well, instead of making this a fraction, let's make this a negative exponent so that it models this a little bit better. So I would then have t plus 3 to the quantity of to a power of negative 3. So now applying this rule, I still have that 5 times this here. I'm going to add 1 to the exponent. So this becomes the quantity t plus 6 to the negative power of 2 over negative 2, and then there's that plus c. It would be nice to rewrite this so that we don't have a negative exponent. So what I can do is I can take the reciprocal of this to make this positive. Just this part, so this will come down here. So I will have 5 over negative 2 times the quantity t plus 6 squared plus c. And remember, with a fraction, this negative can either be assigned to the top number or the bottom number, but not both. So this would be my final answer here. Again, we want to find an indefinite integral, so I need to remember the plus c. Now looking at this, I see that I have t cubed and a t to the 4th somewhere in here. And it's important to know that if I have a product, which I do, I can't just take the integral of t cubed and then multiply it by the integral of whatever else is remaining. There's not a rule for integrating products like this. So instead, I should recognize that I will want to use a u substitution here. Now, I want to use a u substitution because if I let u be this radicand, the derivative of that is somewhere else in the radicand. That's always what I'm looking for. Generally speaking, we will let u be the the radicand. So u in this case is equal to t to the 4th plus 1. So we are going to let u be t to the 4th plus 1. I think it's helpful to label this as u. So if that is u, then I want to find the derivative of that. So the derivative of u with respect to t is 4t cubed. Then what I want to do is multiply the dt to the other side, so I'm separating the variables. So really, du is equal to 4t cubed dt. And just so you know, I often skip this step and just write this as du, whatever the derivative is, and then dt. So looking at this, I want all of this to be somewhere in my integrand. And I have most of it except this 4. So if I put that 4 in here, then I have everything. Now, I can't just put that 4 in there. I have to undo it on the outside. So 4 times 1/4 is simply 1. So if I put a 4 on the inside, I need to undo it on the outside with that 1/4. And then this is du. Now I think, you know, it looks kind of cheesy to label everything and circle things, but I find it to be pretty helpful. So let's go ahead and see what happens now. So I have that 1/4 on the outside. And then under in here, I have the square root of u du. So with the square root of u, remember we can rewrite this as 1/4 times the integral of u to the 1/2 du. Then to solve this, I can add 1, which is the same thing as adding 2/2. So this becomes 1/4 times u to the 3/2. If I divide by 3/2, that's the same thing as multiplying by 2/3. So I can clean this up a little bit. 2 goes into 2 once and into 4 twice. So this becomes 1/6 u to the 3/2. Oh, don't forget the plus c. And then I want to plug this value for u back in. So I know u was t to the 4th plus 1, so I'm going to take that and plug that back in. So my final answer is 1/6 times the quantity t to the 4th plus 1 to the power of 3/2 plus c. And that gives me my final answer. Here's another example. In this example here, I have, I'm basically subtracting two different functions. So in this case, I can integrate this and then subtract it from the integral of this. So let's just rewrite this as the integral of 4x dx minus the integral of 2 over the quantity 2x plus 3 squared. So to solve this, what I'll do is I'll just integrate each of these pieces individually. So let's go ahead and do that now. Integrating this, I simply get 2x squared. Easy peasy. Now over here, this is going to take a little bit more work. I think it might be helpful to rewrite this in a little bit of a different way. So if I rewrite this, let's write this as the integral of 2 times the quantity 2x plus 3 to the negative power of 2 dx. Now looking at this, I have a couple different possibilities to solve this. You can move the 2 out in front, then you can use, to integrate this, you can use the general power rule for integration. You can use a u substitution, a couple different choices. So for me, what I'm going to do is I'm just going to use a u substitution so that we can have a little more practice with that. And I'm going to let u be equal to 2x plus 3. So that means du is equal to 2 dx. So if this is u, I'll notice that all of this is also in my integrand right here. This is du. So this becomes the integral of u to the negative power of 2 du, which then becomes u to the negative power of 1 over negative 1, which is negative 1 over u. So all of this should be rewritten with the x in it, so negative 1 over 2x plus 3. So let's put this all together now. This first integral was 2x squared minus the second integral, which is this. It's a negative, so remember a double negative becomes plus a positive. And then don't forget, since we have an indefinite integral, we need a plus c. So that is the final answer. I think you'll have a lot of fun with this one. Again, since we have addition or subtraction, we can separate this and integrate each part separately. So this will become the integral of 1 over 9x minus 5 dx minus the integral of 1 over 9x plus 5 dx. So these just have a very, very slight difference. One has a minus, the other has a plus. So just like before, I'm going to integrate each of these separately. So let's just draw a line. When I integrate this, I would again use a u substitution. Typically when we use a u substitution, the denominator would be a good place to start when deciding what u should be. And again, when you decide what u should be, its derivative needs to be somewhere in that integral. So let's take a look here. Let's let u equal 9x minus 5. If u is 9x minus 5, then du is 9 dx. Now, I know this is u. The problem is du is not all here. I only have the dx. So, like I did in a previous example, I need to include a 9 here, but I need to undo it on the outside. And that will be undone by multiplying by 1/9. Because if I take this 9 out, because it's a constant, and multiply it by 1/9, it goes away. So this is du. So now I have the integral 1/9 times 1 over u du. Recall that this is equal to 1/9 times the natural log of the absolute value of u. I'm going to go ahead and plug u back in. So I now have 1/9 times the natural log of the absolute value of 9x minus 5. Now I'm going to have the exact same type of thing on the other side. Here, I'm going to let u equal 9x plus 5. So this is u. That means du is 9 dx. Again, I don't have that 9, but I can make it and undo it. So now I have 1/9 times the integral of 1 over u du, which is equal to 1/9 times the natural log of the absolute value, of u. And this is 1/9 times the natural log of the absolute value of 9x plus 5. Okay, so putting it all together, I have 1/9 times the natural log of the absolute value of 9x minus 5 minus 1/9 times the natural log of the absolute value of 9x plus 5. Now we can clean, oh, and I need a plus c. Sorry about that. We can clean this up a little bit by identifying a GCF of 1/9 and then multiplying it by applying properties of logarithms. Hopefully you remember some properties of logarithms. If I am subtracting a logarithm with the same base, I can write this as a division problem. Let's do baby steps. So natural log of this over this. And if both of these are absolute values, then I can write it as a single absolute value. And this will be my final answer. Don't forget the plus c on the end. Here's another example. This is the indefinite integral of cosecant pi over x, cotangent pi over x. Now, one thing you can do is look at your list of basic integration rules. And if you look at that basic list of integration rules, you will find that number 17 shows you the integral of cosecant of u times cotangent of u du is negative cosecant of u plus c. So you can apply that rule if you recognize it. Otherwise, you can certainly use a u substitution. If you use a u substitution, you will want that to be the integral. I'm sorry, not the integral, the argument of the trig function. Now the problem here is that u in this case is a function. It's pi over x. So you might want to use a u substitution in order to help with that. It's really up to you, but you need to understand that you'll basically take the derivative of that and then divide in order to get the final answer. So there are a couple ways you can do this. Let me just show you what I mean. So I'm going to let u equal the argument. If u is pi over x, then du is pi dx. Sorry, hang on. There was no one there, if you could believe it. Anyway, so du is equal to pi dx. All right, like before, this is u, this is u. I'm going to plug in a pi, undo it on the outside. So this will now look more like number 17. So I have 1 over pi times the integral of cosecant of u. Why do I always do that? Cotangent of u du. So applying this formula, I have negative 1 over pi times cosecant of u plus c, and then I'll just plug that u back in every time. And this is the final answer. Not too bad. This example is a little bit more complicated. It's more complicated because of the denominator. Now, if I want, I can take this 4 and move it out in front because it's a constant. So if I do that, then I'll have 1 over 3 minus e to the x dx. Now looking at this, I can't think of any general rule that comes to mind when looking at this denominator. A u substitution right now won't work because the derivative of this is not anywhere else in my integrand. So what I need to do is a little bit of algebraic manipulation in order to be able to use a u substitution. And here's how this will work. What I'm going to do is I'm going to just take this integrand and multiply it by 1. Because if I multiply 1, nothing happens to it. Everything remains the same. The catch is I'm going to multiply by a fancy one. So I'm going to multiply the top and the bottom by e to the negative x. Because that's like multiplying by 1. If I multiply the top and the bottom by e to the negative x, my integral becomes the following. 4 times the integral of e to the negative x over 3e to the negative x minus 1 dx. Now, just so you know, this minus 1 comes from the same bases. Adding the exponent gives me e to the power of 0, which is 1. Okay, so now if I look at this, now if I let u be this, I can see that du is also in my integral. So what I'm going to do is I'm going to let u equal the denominator, which is 3e to the negative x minus 1. If that's u, then du is negative 3e to the negative x. So again, I keep it and divide by the derivative of the exponent, and then dx. And sure enough, everything I need is here except that negative 3. So remember, I'll multiply this by negative 3 and undo it on the outside by multiplying by its reciprocal. So now I have a negative 4/3 times the integral of 1 over u du. If you need to see this, this is u, this is du. All right, so integrating this, I get negative 4/3 times the natural log of the absolute value of u plus c. This is u, so I plug that back in. Negative 4/3 natural log of the absolute value of 3e to the negative x minus 1 plus c for the final answer. All right, take a look at this bad boy. I thought I'd save this one for last because there's a lot going on in this particular problem. So the first thing you want to do is kind of compare it to your basic integration rules chart. If nothing stands out, you want to think, okay, can I separate it into multiple integrals? If it's multiplication or division, you can't separate it into multiple integrals. That's only if it's addition or subtraction. So if that doesn't work, you want to think, okay, can I use a u substitution? Well, in this case, you can't use a u substitution yet because typically you let the integrand equal u. In this case, if this is u, then the derivative is 8x minus 8, which is a little bit more advanced than this. So it's a bit more complicated. So similar to the last example, what I want to do is manipulate this algebraically so that it will look like something in my basic integration rule chart. So here's what I'm going to do. I am going to complete the square on this little bit here. That's right, we're going to take you back to algebra and you're going to love every second of it, I'm sure. So if I complete the square on this, I have 4x squared minus 8x plus 3 equals 0. Okay, so here's how we are going to complete the square. Remember, if I complete the square, I want the x's on one side, so I'm going to move this 3 over. So I have 4x squared minus 8x plus a special number is equal to negative 3 plus a special number. I want the coefficient here to be 1, so I'm going to factor out a 4. Now, we want these special numbers to be the same. And I want you to notice that this special number is going to be multiplied by 4. So since this number is going to be multiplied by 4, I want that same number over here, so I'm going to multiply this special number by 4 also. So in order to identify what this special, sorry, I have an error. This should be a 2. 4 times 2 is 8. Hopefully you recognize that. Sorry about that. Anyway, in order to find this special number, I'm going to take b divided by 2 squared, which is negative 1 squared, which is 1. So 1 is my special number. I want to factor this. When I factor that, it becomes x minus 1 quantity squared is equal to, this becomes 1. I can then subtract 1. So I have 4 times the quantity x minus 1 squared minus 1. Now, food for thought. This is the same thing as saying 2 times x minus 1 quantity squared minus 1, because 2 squared is 4 and this quantity squared is this. Now you might be thinking, why in the world did she just do this? What is happening? What is going on? Well, let's just take some baby steps, all right? Now, I have just rewritten all of this. This is the exact same thing as saying the integral of 1 over the quantity x minus 1, because I didn't do anything with that, times the square root of 2 times the quantity x minus 1 squared minus 1 dx. All right, so what I want you to do is pause this right now and see if this looks like anything on the basic integration rules chart. I hope that you recognized that this looks a lot like number 20 on that chart. So on that chart, number 20 is the integral of du over u times the square root of u squared minus a squared. And this is equal to 1 over a secant inverse of the absolute value of u over a plus c. Okay, so if this is what we are dealing with, let's identify what u is. That's always funny to me. Identify what u is and what a is. So if I do that, in our case here, u is equal to okay, one thing we should mention is that this is u and this should also be u. So they're off a little bit, and what you can do, because there's a 2 here, what you can do is multiply this by 2 and do the same thing here. And so then u is 2x minus 1. And then those 2's will cancel out. But anyway, u is 2 times the quantity x minus 1. A is 1. So throwing this into this here, we get that this is equal to 1 over 1 times secant inverse of the absolute value of 2 times x minus 1 all over 1 plus c. And then this is arc secant or secant inverse, whatever. Arc secant of the absolute value of 2 times the quantity x minus 1 plus c. And this is the final answer. The only other thing worth mentioning here is some different procedures on how to integrate these things. So there's some different techniques, and I talked about some of them, but you might want to take a look at these techniques and examples of how you might want to integrate something. So I talked about some different steps. And if you need to apply some algebraic manipulation, these would be some good pointers to follow. And that concludes section 8.1.